There we go. Okay. We are now recording. Hopefully that will stay in. All right, here we go. Number 1. Okay, so you're determining the oxidation numbers for each of these. So this is 0. This guy is going to be a +3. This is going to be 0, and this is going to be a -1. Okay, so Al is going to give off 3 electrons and become Al 3+. F is going to plus electron is going to then form into, F -1. Okay. Now, in order for this to work properly, we have to get these to be the same number of electrons. So I'm going to take this guy and I'm going to multiply him by 3. So he's going to become 3F plus 3 electrons yields 3F minus. I still have that guy. I'm just not going to take the time to rewrite him. We're going to combine these equations together then, now that these electrons will cancel out, and our overall equation will then be Al plus 3F. Does that add up? No, that is not right. That's F2, so that does not work. Hold on. Hold on. I got it. Just chill. We good. We good. We good. We good. Well, this is F2. Okay. Plus 2 electrons is going to give you 2F minus. There we go. Okay, this is looking better. Okay, so now this does not match this. So we find the least common multiple between these, which is 6. So we want to multiply this by what to get to 6? 2. And we want to multiply this by what to get to 6? 3. All right. So 2Al yields 6 electrons plus 3Al3 plus. And then here we've got 3F2 plus 6 electrons is going to yield 6F minus. All right. Now, these cancel. And we're going to get our overall reaction here, which is 2Al plus 3F2 yields 3Al3 plus 6F minus. Oh, is that 2? I'm sorry. My bad. All right, better? And that balances out here because we've got 2 times 3 would be 6. This is 2, just like it says up there. We would need to balance this side of this equation. It wasn't balanced correctly to begin with, so. Yep, but you have to, the key is that you've got to make sure that these balance, okay? Because when we get into Unit 9, if you don't have the ability to get this stuff to balance out properly, you need this value for calculations in Unit 9, Okay. Right now, you're like, well, this is just a waste of time because I could just balance this stupid equation and come up with this, you know? But the thing is that when you get into Unit 9, you've got to know this value. If you don't, you're not going to be able to do anything with some of those calculations. This isn't a Brinkelhoff, though. This is a compound right here. Are you asking about this one? Splitting this one? I can't. This is not a Brinkelhoff. It's part of a compound. Because for every one of these, I'm going to have 2 fluorine ions. And those 2 fluorine ions are going to end up going together with this guy and making this ionic compound. Okay. All right. So Hg here, this is a +2. This is a -2. This is 0, 0. So here, Hg +2 is going to pick up 2 electrons, and he's going to become Hg. Oxygen then, which is a 2-, is going to give off 2 electrons and form O2. This would be 2 of these. So they would actually be given off, is that right? 4 electrons, right? Hmm. Yep. Yep. That's it. Okay. Good job. Thank you, Esther. I think it was Esther. So I'm going to take this, I'm going to multiply it by 2. So once I multiply it by 2, this is going to be a 2. This will be a 4 then. And this will be a 2. Good job. Okay. So then this cancels out. That leaves me with 2Hg plus 2 plus 2O2 minus yields 2Hg plus O2. Yep, everything balances. All right, good? Yes, ma'am. Here, because that's from this right here. Because I need 2 of them. Because I have O2 over here, I've got to have 2 over here to get that to work out if I want to have O2 over here. So for our Unit 9 calculations, we would have 4 electrons. Okay, again, I am putting the cart before the horse, but I want you to understand when we get in there how important that's going to be. Because that's going to help us understand how many coulombs of energy per joule, coulombs per joule, or electrons per joule, or yeah. So we got to do all of that stuff when we get into Unit 9. What? All right, here we go with another one. All right, so here we've got our ions. This one should be a little easier. So get rid of that guy. Control Z. Back to my pen. So Cu 2 plus 2 electrons is going to give me Cu, and Al yields Al 3 plus 3 electrons. So again, lowest common multiple is 6. So I'm going to go through, I'm going to multiply this all by 3. So this becomes a 3, this becomes a 6, and this becomes a 3. I'm going to multiply all this by 2. So 2, 2, and 6. So then my electrons cancel, and that leaves me with my overall equation of 3Cu2 plus 2Al yields 3Cu plus 2Al 3 plus. Because see, this appears to be balanced up here, but it's not because we haven't balanced our charges. So that's why you've got to go through all of this to get to this. Can carbon be a +2? Yes, it can. Okay, so here we've got our zinc. He is going to add N 2 electrons to become zinc. We've got our carbon, who is going to give off 2 electrons to become C plus 2. These are already balanced, so that makes life easier for us. So this becomes Zn2 plus C yields Zn plus C plus 2. Easy one? Yep, because its oxidation number is not changing at all. Matthew? Or Haley, sorry. I just saw a hand. Yes, go ahead. 0, and then this is a +1. This whole thing is a -1. We could go into those individual things, but since it stays as nitrate over here, its oxidation number is going to stay the same. So no change there. This should be a +2 here, and this is a 0. All right, so here we've got zinc. Zinc is giving off 2 electrons to become zinc 2 plus. That silver then is going to pick up an electron to become Ag. These are not balanced, so I need to go through and balance them. So I'm going to put a 2 here, a 2 here, and a 2 here. Now they'll cancel, and then I write what's left over. Questions? Yeah. Nope, just 1 per stand. They only need 1. They're not doing an acid base. So, all right. So that was number 5. Number 6 then. Do you still need 5 up? I don't know. Yes, question. Oh, probably. Yes. Lippy fails again. All right, so here we've got 0. Here we've got a +2. We have chromium is a +3 here and becomes a 0 over here. This guy is a -1, so he's unchanged. So we're just going to look at the zinc and the chromium. So zinc is going to give off 2 electrons to become Zn2 plus. Our chromium then is a +3. It's going to pick up 3 electrons, and it's going to become Cr just by itself. All right, so then we've got to find that least common multiple. So here, that's going to be 6. So we're going to multiply everything on this by 3. and everything down here by 2. That did not work out well. Let's try that again. There. Better? All right. These electrons cancel then we write down what's left over. Let's see if I can do that without messing up. Well, and the answer to that would be no. Plus 3 yields 3Zn plus 2Cr. All right. Hopefully that looks right. And I think we got a couple more. Do you guys want me to go through a couple more, or are you feeling good about these? You want me to move on to the progress check and talk about that then? Okay. All right. So progress check I have over here. Here we go. All right. So you had the answer key available to you. So let me know what you have questions, what you want me to talk about on there. That was actually the published answer key from AP Central, so there shouldn't be any errors in it, as opposed to the stuff that I do. Matthew. So when they're talking about a neutralization reaction, they're talking about an acid-base reaction. And so when they're doing that, you're going to end up neutral. If you have a hydrofluoric and you have sodium hydroxide, you're going to end up at a point where you're going to have those neutralized. Your H plus is going to equal your OH minus at a certain pH. And that's what a neutralization reaction is. And so they want to know which one of these is the correct net ionic equation for that. Yep. Yep, and it's not reacting, it's not doing anything. So you want to find the stuff that ends up being your acid and base when you're doing this. So for this, you've got your H here, HF. This is going to be your acid on this side, making this your conjugate base. So you always want to make sure that you have your acid and your conjugate base and your base and your conjugate acid listed in those neutralization net ionic equations. So you need to show, just like with our redox reactions, you have to show how the charges change with the oxidation numbers. You have to show which one of these is donating a proton and which one's receiving that donation on the other side. So this one is here. Yeah. Yeah, the chlorine's going to stay. Yeah, and it's not donating or accepting those yeah, because this is what's doing that, is this guy. Yeah, Jaden. Mm-hmm. Well, right, but they're asking about like what is happening here in terms of neutralization. Okay, so at that point they're telling you this is an acid base, so you need to focus on what is donating that hydrogen. So if this is donating that hydrogen, over here something's receiving it, so you're showing what that trade-off. So when they want to have a net ionic equation of a neutralization or an acid base, you need to make sure that you're including both the acid, the conjugate base, the base, and the conjugate acid. Yep. But these, I don't know that the oxidation numbers are necessarily changing here, so I don't know that that's a case here. But that's the case of a redox reaction. Redox is where your oxidation numbers are going to change. Okay, so that's a redox reaction. Acid-base, instead of transferring electrons, as in this, here you're transferring the hydrogen proton. And so you want to include all those places that that hydrogen has been transferred. It came off of here, so we need to still show this guy in that process. Yeah. All right. Excuse me. So when we're doing number 11, you're noticing that this is going to be another one of those acid-base reactions. We've got that between acetic acid and we have it between sodium hydroxide. Okay. And they're asking here, says the NaOH added, the equivalence point was reached after a total of 20 mils of this had been added to the flask. How does the amount of this vary after this has been added? So our flask is sitting here, right? And our flask has what in it? This is our acetic acid. So this is our acid. And then our burette is coming in, and this is going to be our base. So initially, we're going to have a large amount of this compared to, as we're dripping our base in, we're going to have a little bit of base in. So they're saying when we have 5 mils, it takes 20 mils to get this to where those things are equal. The H plus equals the OH minus. That's after 20 mils. So we've only got a quarter of the way in at this point. Okay. So they are looking here and they're trying to figure out the equivalence point was reached. How does the amount of this compare to this? Amount compared to when they had 1 mil in. So if we had 1 mil in, there would have been less acid in there, right? And now we've got more of that acid in there. So this is definitely a contender. This would not be, because we would actually have, no, that would, good grief. Okay. Yeah, that's why I rejected that one. Okay. So this wouldn't have increased because we've taken some of this and it's reacted with the base. So we've got less of this now after 5 mils than we did after 1. Okay. It is the same because all the coefficients are 1. That doesn't make any sense. It's at the half equivalence point. You guys don't even know what that means yet, but it makes sense that we're not there yet. If we needed 20 mils and the half equivalence point would be 10. Okay. So that doesn't make sense. And then this one's the only one left. It is less because some of this reacted with the base. And what happened was, if we really look at the equation, what we did here was we had H and then acetic acid. I'm just going to do HA there, plus the NaOH. What you've made over here is you've made water and you've made sodium acetate. Okay. So that's why it's neutralized. And in the process, some of this stuff reacts with this, so you're going to end up with less of this than you did when you had 1 mil added. Excuse me. All right, other questions? Jaden? That the definition of Bronsted-Lowry is wow, I got stuff in my throat. I can't get out. So there's different definitions of acids and bases. Okay. There's an Arrhenius model. Arrhenius was the original one. And what he said was that an acid is what creates hydrogen ions and a base creates hydroxide ions. Okay. But the problem with that is we have something like this going on. There is no oxygen here. So that doesn't work when this guy's a base and we don't have any oxygen to make hydroxide. That doesn't work. So they rejected Arrhenius. And the next guy that came out with something, I think he was the next guy anyway, was this team called Bronsted-Lowry. And what they said was that an acid is a hydrogen donator. So they're going to donate the hydrogen and he's going to donate it over to this guy. And a base then is a hydrogen acceptor. So this would be your base because he's going to accept that hydrogen over onto this side. So if we look at like another, let me see if I've got another equation here that's better to work with. Yeah. So here, I guess this is the equation. They just have it written out. Okay. This is my hydrogen donor. He's donating it to the water. And this is going to be my hydrogen acceptor. Yeah. So this, oh yeah, this is my hydrogen acceptor. He's going to accept it on this side. So this is my acid. This is my base. This would be my conjugate base. No, my conjugate acid, excuse me. Conjugate acid. And this would be my conjugate base. Because then he's going to turn around and accept the hydrogen from this guy and become this. And it just keeps feeding on itself back and forth. There are other definitions of acids and bases. I believe the other main one is Lewis acids and bases. And if you get into college, you probably will study some of those when you get into more of your advanced coursework. Isabella? Mm-hmm. Yep. Okay. So this could get another hydrogen and become H2S, or it could give another hydrogen away and become S2 minus. This guy could accept another hydrogen, okay, and become acetic acid, but he has no ability to give another hydrogen away. Okay, because if you draw this out, the carbon has these hydrogens here. Okay, he's not going to give those hydrogens away. That's not going to happen. So he can't be our answer because he can't give another hydrogen away. This is a base and it can't give any other hydrogen away. It can accept another hydrogen and become acetic acid, but it can't give another hydrogen away. On this one, probably not, but I think that they would probably give you, I don't think that they would give anything that complicated. Here, it can't take another hydrogen in. It could give one away, but it can't give another hydrogen in. Take one in. So it can't be in a base. And then this one, the same holds true. It can't take another hydrogen in. So it can't be a base. Because a base is a hydrogen acceptor. This is an acid. It can give one away and become NH3. Because there's no other positions available for another hydrogen to come in. You're looking at something like this right now. Nitrogen doesn't have any other spots there that you could add anything in. It's got full octet all around. It can't expand its octet. So where are you going to add a hydrogen in? You can't add it to any of these other hydrogens. They can only have one bond. So how are you going to make that happen? You can't. So this can't add another hydrogen in. It can't either. Oh, those aren't O's, those are H's. Yeah, it's got this, it's a +1 charge. I don't know, I gotta think on that one. Oh, yep, yep, that's right. Yep. You're good? Okay. I don't do well thinking on my feet, guys. I really don't. Yeah, yeah. Okay, so this is a half reaction one. So, this is tin and aluminum. So I've got to go through and I have to multiply by my, I got to multiply this by 2 and this by 3. Once I do that, I'm going to be getting rid of electrons, right? So I need to look for one here that doesn't have any electrons in it. So this one has electrons still, so he's gone. This one has electrons in it, so he's gone. So I've got 2 down now. We've got to figure out what's going to be next. Well, this one, we have 2 and 3. So they're multiplying that there. Here, they're multiplying the aluminum by 3. So that wouldn't work. So it has to be C. Does that make sense, Matthew? Um, Not necessarily. I mean, I went through and I did the math on this guy personally. So I went through, this is 12. Where's my equation on this guy? I can't. Oh, here. I've got too many things going on here to be able to figure out which mouse controls what and that sort of thing. Okay, here we go. So what I did was when I did this, I looked at it and I went, okay, I've got 100 mils of this because this gets so wordy in here. It was hard to follow like everything. Good Lord, it was just so much, you know? So I needed to kind of break it down. So I did 100 mils here, and this was 0.1 molar. Okay. And then I did 100 mils here, and this was zero point 0.2 molar. So the thing is that I've got twice as many moles here as I have here. I've got the same volume. So I'm just looking sheerly at moles at this point. Both of these are going to run out at the same time. Does that make sense? Okay. Because I'm using this as a 2-to-1 ratio. So when we wanted to go, stop. When we wanted to, they wanted to double it, I believe, if I'm remembering this one correctly. Double, yep. So we want to double this amount here. So what would do that? Well, if I doubled this guy and I didn't touch this guy, no, I'm sorry. Yeah. If I doubled this guy and I didn't touch him, okay, then I'm going to run out of this first and I'm never going to double this because I didn't increase this at all. So I'm getting rid of that. Here, I'm gonna double this, but the problem is that I haven't touched this one, so now I'm gonna run out of this guy first. So I'm getting rid of him. Now they're talking down here about giving me 400 mils of this and 200 mils of this. So that's going to give me more than double this. So that doesn't work. But this guy here, if I double this amount and I double this amount, then that's going to give me double the amount. Well, this is in a 0.1 molar to 0.2 molar. It's in the same ratio, and I've got the same amount. So at this point, I'm going to run out of both of these at the same time. If I want to double this, I double these, and I'm there. Right, I'm going to more than double. And they want to double. Yeah. Matthew? Okay, anybody else multiple choice? Multiple choice is good? All right. Okay. Okay, so according to the equation, if the amounts of the reactions are halved, how is that going to react? So if we half this, what's that going to do to this? Yeah, it's going to go in half. Nope. No, if they don't ask you to explain, do not explain. Okay? Because if you give them the right answer and then you go on to explain it wrong, they will mark it wrong. Yes, just like that wavelength question that they asked you about last test, okay, with the copper and the other one. There, they asked you for the value, you write that value down, you move on. Do not explain. Number one, if you get it wrong, they will mark it wrong. Okay, the explanation. Number two, you're wasting time that you don't have. Ksenia. Okay, which one's accepting the proton? So here, this is my extra proton for here. So this is my acid, this is my base, this is my base, and this is my acid. So my OH is going to accept this OH and become this guy. G is in golf. Okay, so here they've got 20 mils instead of the 10, I believe. So that means that you're going to have to add in twice as much of this to neutralize it. The neutralization point is still going to be at 7. So I'm going to draw a little point here just to help me out. And then I'm going to start out at 1 or less because that was a strong acid. And I'm going to, oops, that's not a good curve. Okay, let me start it this way. I'm not an artist, you guys. I don't know if you've picked up on that yet or not. There, that's better. And then here, I need to finish here in the same spot. I need to have that straight portion. There we go. That's looking a little better. Yeah, so you are taking a strong acid. So a strong acid is going to have a pH of 1 or less. and you're reacting it with a strong base, which means that your pH at the end is going to be 13 or greater. So because of that, you know that your pH is going to start out down here. If it's a strong acid, strong base, and you'll learn this part later, but if it's a strong acid, strong base, the neutralization point is 7 for the pH. And so you need to make sure that you're starting here. You've got your straight point here with the middle of that straight point coming in at 7. You see how theirs looks nice here? They've got that straight point is right here, and the very middle of that straight section is 7. That's what you want. I am not a great artist, so I do my best. Why is it at 7? What? Because that is the question G said that we doubled the amount. You no longer have 20 here. You've now got 40 or something like that. Something doubled, and so then this has to double. Yeah, they must have doubled this to 40. All right, see you Monday. Cool, thank you.